Hello, and welcome to Chapter 2 of our course MEC260 on Engineering Statics. My name is Jay Mendelson. I'm a lecturer in the Department of Mechanical Engineering. This week you're going to read Chapter 2 in our book Vector Mechanics for Engineers, and we have two homework assignments for you to do in Connect. That's homeworks number 1 and 2. I wanted to introduce you to some members of your class. There's me on the left, and on the right we have Oliver, Woody, and Jesse, and you know who's in charge of this class. Some days your classmates are very, very intense, and they really learn their vector mechanics. Other days, not so much. Looks like this crew's going to need some extra credit to catch him up. We're going to do a 2-minute rapid review of Chapter 1, which is going to double as your 2-minute review of freshman physics. We're going to go over Newton's first, second, and third laws. Newton's first law says if the resultant force acting on a stationary body is 0, the body remains at rest. And if the resultant force is 0 on a moving body, then the body will continue to move at a constant speed in a straight line, just like this aircraft shown in the diagram below, where the thrust force moves it forward, the drag force retards the aircraft, and if the thrust force equals the aircraft flies at constant speed. Newton's second law says if the resultant force acting on a particle is not 0, the particle has an acceleration proportional to the magnitude of the resultant and in the direction of the resultant force, otherwise known as F equals ma. So here's your cart, and it has a little mass on it. You put a force on it, and it's going to accelerate very rapidly. And in our little red cart, you put a big mass on it, and the same force, well, it's going to accelerate very slowly. Newton's third law says the forces of action and reaction between bodies in a contact have the same magnitude, the same line of action, and the opposite sense, otherwise known as for every action, there's an equal and opposite reaction. And then Newton did his famous gravitational law that says if two particles of mass capital M and small m are mutually attracted, the equal and opposite forces F are given by this formula. F equals G, where G is the gravitational force, times capital M times small m divided by r squared, where r is the distance between objects. Now you've got freshman physics back in your head again. So it's time to start our class in vector mechanics. First off, a force is defined by its point of application, magnitude, and direction, which we see down here in the lower left in figure 2.1a. And the direction is given by our line of action and the sense of the force. The length of this arrow, which is denoted as 10 pounds, represents a magnitude, and the line of action is defined by the angle of this arrow with a fixed axis. In this case, the fixed axis is the x-axis, and we're at a 30-degree angle. Two forces having the same magnitude, same line of action, but opposite sense have opposite effects on a particle, which is shown here in figure 2b. This force has exactly the opposite direction, but the same magnitude as the force in figure 2.1a. Transmissibility says that the equilibrium of a rigid body remains unchanged if a force acting on the body is replaced by another force of the same magnitude, direction, and line of action. So here's our rigid body in the lower left. There's our force F and our line of action. And we can move force F along this line of action and get force F prime, where F prime has the same line of action, same magnitude, but it has a different point of application because we moved it backwards along the line of action. Here's some vector terminology for you. Vectors represent forces. Their symbol is an arrow in a diagram with a boldface type. So let's look at our vectors here in the lower left. We've got our arrow and we've got our boldface p. Fixed vectors cannot be moved, and free vectors can be moved freely in space, for example, a couple that we'll talk about in Chapter 3. Sliding vectors can be moved along their lines of action per the previous slide. Equal vectors have the same magnitude and direction, but different points of application. And these equal vectors, of course, have to be parallel to each other. Equal and opposite vectors, shown here in the lower right, have the same magnitude, opposite directions, and different points of application. So we've got plus p going from the lower left to the upper right, and we've got minus p going exactly in the opposite direction from the upper right to the lower left. The parallelogram law for the addition of forces says that two forces acting on a particle may be replaced by a single force, which is called the resultant. And you find the resultant by drawing the diagonal of the parallelogram with the sides equal to the given forces, as shown here in figure 2.5. So we've got vector p in red, vector q in red. We draw this dotted line, which is parallel to p and starts here at the end of the arrow of q. Likewise, we draw this dotted line, which is parallel to q, starts at the end of the arrowhead for p, and where it intersects those two dotted lines is where we're going to draw the resultant. And we take this resultant, which is equal to p plus q, and we start it out at particle A, which is where p and q act, and we draw it here across the diagonal of the parallelogram to our point. Now the magnitude of vector p plus q does not equal the algebraic sum of the magnitudes of vectors p and q unless p and q are equal and opposite directions. And the addition of vectors is commutative, which means that p plus q does equal q plus p in vector speak. The triangle rule says you can sum two vectors p and q by arranging them in a tip-to-tail fashion. You may connect the tail of q to the tip of p, as shown here in figure 2.6a. So there is the tail of q, there's the tip of p, and we move q from where it started here at point A, and we move it such that it starts at the tip of p and goes for its length. And then p plus q starts at A and finishes off where the tip of q is. Likewise, you can connect the tail of p to the tip of q. So in this case, we start with q, and we connect the tail of p here, and we move it up. And then p plus q starts at point A, and it ends at the tip of vector p. Here's another way of looking at vector addition. Vector p plus q equals the tangent to Jesse's tail. You can subtract vectors too. You use the method for the addition of vectors, but with the negative of the second vector. And you determine the vector p minus q by adding p to the negative of vector q. So here's p, and there's p in red. And instead of bringing q over such that the tail of q goes from the tip of p and extends in the direction shown by plus q, we bring q over, but we go in the opposite direction, so that it's negative q. And then p minus q is found from the triangle rule from the prior slide. We draw it from the point of application of p and q, and we go up to where it hits the tip of the vector minus q. We add 3 or more vectors with the polygon rule, which is an extension of the triangle rule. we find the sum of three vectors, p, q, and s, or more, by arranging them in a tip-to-tail fashion as shown in figure 2.8b. So here is p, and then q starts at the tip of p, and then instead of closing the triangle from point A to the tip of q, we then bring in vector s, and s starts from the tip of q and goes down and to the right, and then p plus q plus s starts at point A and then goes to the tip of s. Alternately, we can repeatedly use the triangle rule. First, we add the vectors p plus q, and then to get vector p plus q, creating a triangle. Then, where the tip of p plus q is, which of course is the same place as the tip of q, we bring in vector s, show it going down to the right, and then the vector p plus q plus s is drawn from point A to the tip of s. The vector p plus q plus s is going to wind up of the same line of action and the same magnitude, whether you use the polygon rule or whether you use the triangle rule twice. Vector addition is associative. We can add the vectors using the polygon rule in any order, and that's shown here in figure 2.8d, where we show that p plus q plus s is equal to vector s plus q plus p, because putting those vectors in the different orders tip to tail still brings you back to the same point, which is the tip of the vector p plus q plus s. Now we'll show you how to take the product of a vector and a scalar, where a scalar is defined as just a number, where the number could be an integer, or it could be fractional, or it could be decimal for that matter. And as per arithmetic, adding two vectors p plus p is also equal to 2 times the vector p, and adding vector p plus p plus p is equal to 3 times vector p, which means that the sum of n equal vectors p is equal to np, where np has the same direction as vector p, but it has the magnitude of n times the magnitude of p. The product kp of scalar k and vector p has a magnitude equal to the product of p and the absolute value of k. And the direction of vector kp has the same direction as p if k is positive, or the opposite direction if k is negative. So here's vector p in the figure. We multiply by 1.5, and the length of the arrow gets 1.5 times greater, and it's still in the same direction as the original vector p. And here's the vector minus 2 times p, and that vector is twice the length of the original vector p, but it's pointed now in exactly the opposite direction. Concurrent forces are defined as forces that all act at the same point, as shown here in the lower left in figure 2.10a. If the forces at point A are coplanar, you can add them via the polygon rule, where p plus q and plus s is going to equal vector r, and vector r is found by drawing an arrow from A, where point A is where the original three vectors act, to the tip of S. Vector R represents the resultant of these concurrent forces, P, Q, and S, and the associative rule also applies to concurrent forces, such that P plus Q plus S is equal to P plus Q, and then add s, and it's also equal to p plus the vector q plus s. Now we'll show you how to resolve force into components. Force F may be replaced by two or more forces that have the same effect on particle A. The resolved forces are components of F. So here we've got force F acting at point A in figure 2.11a, and we can resolve that into the forces Q and P that are shown in blue. But force F can be resolved in an infinite number of ways, as shown in figure 2.11b and 2.11c. But the most common method of resolving a force F into two or more vectors is to align these components. For 2D, it's just two vectors, P and Q, with the x and y coordinate axis. If we were to resolve force F into three axes, then we would use the x, y, and the z axes. There's a few ways that you can resolve forces. First way is that force F and one component P are known, and you want to find the second component, in this case Q, which is shown here in the lower right in figure 2.12. So you would draw force P in space, and you draw force F in space, and F is equal to P plus Q. And the way you find Q is you use the triangle rule, but you use it by drawing the vector Q from the tip of P to the tip of F. Because if we were trying to find F and we had P and Q, then we would draw Q from the tip of P, and then we would draw vector F from point A to Q. But in this case, we know F, we know P, we're just trying to find Q. We can solve for the magnitude and the direction of Q by trigonometry because we know the lengths of P and F and we know what their angle is between these two vectors, and we can use our friends the law of sines and the law of cosines to find Q. Now, if force F and the line of action of P and Q are known, meaning we know what axes we want to draw Q along and P along, then we would apply the parallelogram as we see here in figure 2.13. We would draw lines through the tip of F that are parallel to the lines of action. So here's point A, there's F, there's the tip of F. We draw this dotted line that is parallel to this first line of action. We draw the second dotted line intersects our first line of action. Then Q goes from point A to where our upper dotted line intersects our first line of action, and P goes from point A to where our second dotted line intersects the second line of action. Here's sample problem 2.1 for the resultant of two forces. Here it says that two forces P and Q act on bolt A. Determine their resultant R, where there's a 25-degree angle between Q and P. Q is 60 newtons, P is 40 newtons, and P makes a 20-degree angle with the horizontal. Step 1, we have to apply the triangle rule to forces P and Q in order to find their resultant R in space, meaning to plot it. So here we have point A, there's vector P, vector Q starts at the tip of P and goes in space at an angle, and then vector R here graphically is shown from point A to the tip of Q. And we know that vectors P and Q with respect to each other make a 25-degree angle, and we need to figure out what this angle alpha is in the diagram on the bottom so we can figure out the direction of R. In step 2, we determine obtuse angle beta from this triangle. Now we know that P made a 20-degree angle with the horizontal, so there's our 20-degree angle. And we know that P and Q made a 25-degree angle with each other, so if we show this extended dotted line of P, there's our 25-degree angle. And we've also graphically drawn our triangle with vector R. Well, if you study this triangle, you see that 25-degree angle is an outside angle of the triangle, and 180 minus that angle is going to be obtuse angle B. And 180 minus 25 is 155 degrees. So now we can determine the magnitude of r from the law of cosines, because we know two sides of a triangle and we know the angle that is opposite vector r. So we apply our law of cosines and we see that r squared equals p squared plus q squared minus 2pq times cosine of beta. And we just plug in some values where p was 40 newtons, q was 60, and beta is 155 degrees. And we punch buttons on our calculator and find that r equals 97.73 newtons. In step 4, we determine acute angle A from the law of sines. And that acute angle is this small one right here, which is between vector P and vector R. So that sine A is to Q as sine of beta is to R. And we plug in values for Q was 60 newtons, R was 97.73 newtons, beta was 155 degrees, and we find that this small angle A is 15.04 degrees. And we add that angle A to the original 20-degree angle between vector P and the horizontal, and we see that vector R is at an angle of 35 degrees from the horizontal. This nomenclature shown at the bottom, R equals 97.7 newtons at an angle of 35 degrees to the horizontal, is the standard nomenclature for the magnitude and direction of force. Here's an Excel solution for you showing you how I got all my numbers. Some of you guys may want to use Excel to do your homework in McGraw-Hill Connect website, and for that reason I post some solutions, or at least screenshots of solutions of how I did the work in Excel as a way to organize your thoughts. Sample problem 2.2 teaches us how to resolve a force into its components. In this problem, two tugboats are pulling a barge, as shown in the diagram on the bottom, and the resultant of the forces exerted by the tugboats is a 5,000-pound force, which is exerted along the axis of the barge, so it's basically the horizontal axis. And our assignment is to determine the tension in each of the ropes if this angle alpha is 45 degrees. The value of alpha for which the tension in rope 2 is the minimum it's going to get, and the tensions in the ropes when the tension in rope 2 is at that minimum. So in step 1, we apply the triangle rule to find forces T1 and T2, where T1 means the tension in rope 1 and T2 means the tension in rope 2. Notice we've drawn in our 45-degree angle and our 30-degree angle in this picture. And by symmetry, the 30-degree angle in the triangle at the top between T1 and the horizontal becomes this 30-degree angle here on the bottom with our dotted line and our vector, which is 5,000 pounds. Likewise, we have our 45-degree angle with vector T2 and the horizontal 5,000-pound force, because alpha is said to be 45 degrees. And we create our force triangle from one of the two triangles shown in the picture, in this case the bottom one. The angle between T2 and T1 is 105 degrees because 180 minus 45 minus 30 equals 105 degrees. And we can determine the magnitudes of T1 and T2 from the law of sines, where T1 is to 45 degrees as T2 is to sine 30 degrees, as our 5,000-pound force is to its opposite angle, which is 105 degrees. And we plug buttons in on our calculator. We get T1 is 3660 pounds and T2 is 2590. In step 4, we study the triangle and we imagine how will T2 vary if you increase or decrease this 105-degree angle. Well, let's study T2 and imagine what happens if we increase this 105-degree angle. If we increase that angle, that means alpha has to get smaller, so that T2 starts rotating in the clockwise direction, and it's going to have to get longer in order to meet T1, because it has to rotate in this direction, which means T1 is going to get shorter, T2 is going to have to get longer. In the other extreme, imagine 105 degrees gets to be a smaller angle. Well, if this gets to be a smaller angle, that means alpha gets to be a bigger angle. And what's going to happen is T2 is going to shrink as it rotates clockwise. T1 is going to get bigger, but that's okay. And once you hit 90 degrees, you're going to get a right triangle. And if you keep rotating clockwise, T2 is going to have to get bigger again. So T2 is minimized when you have a right triangle with alpha equal to 60 degrees. Our 30-degree angle, of course, was fixed. And this angle right here becomes a right triangle. And when we recalculate the magnitudes of T1 and T2, we find that the tension in the rope T1 becomes 4330, T2 is 2500, and before T2 was 2590, but when we decrease the angle here to 90 degrees, T2 came down to 2,500 pounds, which is its minimum amount. Here's an Excel solution showing how we work through all of these numbers. Unit vectors are used to define forces in their x and y directions. Unit vector I has a magnitude of 1 with a direction along the positive x-axis, as shown in the lower left in figure 2.16. And unit vector j has a magnitude of 1 with a direction along the positive y-axis. Figure 2.14 shows how we define forces in terms of unit vectors. Force F is shown acting at angle theta to the x-axis. The x component of the force is shown in bold as capital F sub x, and that's equal to F sub x in italics times I, where F sub x is a positive or negative scalar. F sub y, shown in bold, is the force component of F that acts along the y-axis, and it's equal to F sub y in italics times j, where F sub y is also a positive or negative scalar. And then we define force F as equal to F sub x in italics times I plus F sub y in italics times j. F in italics is the magnitude of force F, as shown in figure 2.17, and theta is the angle between force F and the x-axis measured counterclockwise from the positive x-axis. F sub x in italics, meaning the magnitude, is equal to force F times cosine of theta, and F sub y in italics is equal to force F times sine theta. Tangent theta is equal to F sub y in italics divided by F sub x in italics, and F in italics is the length of the vector that represents force F, and that's equal to the square root of F sub x in italics squared plus F sub y in italics squared. Here's a concept application 2.2 for scalar components. A man shown in figure 2.19a pulls with a force of 300 newtons on a rope attached to the top of a building. What are the horizontal and vertical components of the force exerted by the rope at point A? And notice point A is in the upper right corner of the building. Normally you would attach a pulley or a bracket to that point when you're pulling on the rope. In step 1, we determine expressions for the x and y components of that force denoted as F sub x and F sub y. F sub x is the 300 Newton force times cosine alpha, where alpha is the angle between the force and the horizontal, and F sub y is minus 300 newtons times sine alpha. F sub y is a negative number because that y force is pointed in the negative y direction according to the coordinate axis that we've drawn in the lower left corner of figure 2.19a. In step 2, we find the length of line segment AB, which is the hypotenuse of a triangle with one side having 6, meaning the vertical side, and the horizontal side has 8 meters. And from the Pythagorean theorem, the length of AB is equal to the square root of 6 squared plus 8 squared, and that's 10. So it's a 6, 8, 10 triangle, which is the same geometry as a 3, 4, 5 triangle, which means that cosine of alpha is equal to 8 over 10, which is 4/5, and sine of alpha is equal to 3/5. In step 4, we solve for f sub x and f sub y, their magnitudes, and write it in terms of the unit vectors. F sub x is equal to 300 newtons times cosine alpha, or 4/5, that's equal to 240 newtons, and f sub y is a minus 300 newtons times sine alpha, that's 3/5, which is minus 180 newtons. And therefore, force F, shown in bold at the bottom, is equal to F sub x in italics, which is 240 newtons times I, minus 180 newtons, which is F sub y in italics, times J. Here's an Excel solution that I did for this concept application 2.2 that you may find useful. This slide will show you how to add planar forces by summing their x and y components. Previously, we showed you how to add forces using either the triangle rule or the parallelogram law. Forces S, P, and Q all act at point A, as shown in the lower left in figure 2.21a. In figure 2.21b, we resolve all the forces, P, Q, and S, into their x and y components. In figure 2.21c, we add the x and y components algebraically, meaning add all the x's, add all the y's together, to obtain the x and y components of resultant R. And in figure 2.21d, we apply the parallelogram law to configure vector R, which is equal to Rx times I plus R sub y times J. We also show you the standard formula. If vector R equals vector P plus vector Q plus vector S, then Rx times I plus Ry times J is the sum of the x components, Px plus Qx plus Sx times I, plus Py plus Qy plus Sy times J. Here's sample problem 2.3 to illustrate how you sum planar forces using the method just described. 4 forces act on bolt A, as shown in this diagram. Determine the resultant of the forces on the bolt. In step 1, we find the x components of the forces and sum them. So for each of these forces, F1 to F4, we define their magnitudes, which are 150, 80, 110, and 100 respectively. And then we show the formulas that we use to find the x components of the 4 forces. And notice that we have to take the cosine of the angle as defined relative to the positive x-axis. For example, even though F4 is shown as only 15 degrees from the x-axis, we want to use the cosine of 345 degrees to multiply the magnitude of 100. For F2, we give it the minus 80 times cosine of 110 degrees because the minus sign indicates that that force is going in the negative x direction, knowing that the cosine of 110 degrees is a positive number. We multiply out all the values and show it in the fourth column at the right, and r sub x is equal to 199.1. In the next slide, we do the same thing for the y components. And note that we're using 150 times sine 30 degrees. That's a positive value. The y component of F2 is 80 times sine 110 degrees, which will yield a positive value. For F3, we can multiply 110 times sine of 270 degrees, because sine of 270 degrees is minus 1, and therefore the y component of F3 will be minus 110. And for F4, we take 100 and multiply it by sine 345 degrees, knowing that sine 345 degrees is a negative number, and that y component comes out to minus 25.9. Algebraically add up the four values in the right-hand column, and we get r sub y is 14.3 newtons, which means that force R is 199.1 newtons, which was our x component, times I, plus 14.3 newtons times j. Now we need to find the angle alpha for the resultant force R. Tangent of alpha is equal to ry over rx, which is 14.3 over 199.1 newtons, and the inverse tangent of that quotient is 4.1 degrees. Now we need to find the magnitude for the resultant force R. We can take it as 14.3 newtons over sine alpha and get 199.6 at an angle of 4.1 degrees. Alternately, we could have taken the square root of 14.3 squared plus 199.1 squared, and we still would have gotten 199.6 newtons. Here's an Excel solution for you showing step by step how we calculate all the values. A particle is in equilibrium when the sum of the forces acting on the particle is zero, which means vector r is equal to the sum of all forces F, and that has to equal 0 in order for the particle to not move, and by Newton's law be in equilibrium. This may occur if two forces have the same magnitude and line of action but opposite sense, as shown in figure 2.22 in the lower left, where a 100-pound force one way opposes a 100-pound force going in exactly the opposite direction. It may occur for three or more forces shown in figure 2.23a, which shows this graphically. Figure 2.23b shows this per the polygon rule, because when we lay out our four forces, F1, F2, F3, F4, and show them in tip-to-tail fashion, these vectors take us all the way back to the origin, meaning that resultant vector r, by definition, is 0. Algebraically, we can sum each of these vectors, saying summation of f sub x times I plus f sub y times j equals 0, knowing that that equation is equal to the sum of all x forces, summation f sub x times I, plus the sum of all y forces, summation of f sub y times j. We can individually create two equations by summing the x forces individually to 0 and summing the y forces individually to 0. In this slide, we'll show you how to draw a free body diagram, which defines how the forces are arrayed in space. A space diagram is shown in figure 2.24a, where a space diagram is a sketch showing the physical conditions of the problem. So here's a truck, and two guys on left and right are trying to get that big weight off the truck and lift it up in the air. And each of them is pulling down on their respective pulleys. The guy on the left is pulling down on a cable that is on pulley B and creating the force T sub AB between points A and B. And the guy on the right is pulling vertically down on the pulley at point C, which is creating the force T sub AC in between points A and C. And the free body diagram takes those two forces, T sub AB and T sub AC, and shows them in space at their respective angles of 50 and 30 degrees, and also shows the third force, which is the weight of the crate, which in this diagram is defined as 736 newtons. You create a force triangle from the vectors in the free body diagram in figure 2.24c by laying out each of the three forces in their directions in space, but plotting them all tip to tail. So here is vector TAB as a start, and its angle relative to this vertical force coming down of 736 newtons is 40 degrees, because 90 minus this 50 degree angle relative to the horizontal is a 40 degree angle relative to the vertical. Then the downward force of 736 newtons is at an angle with TAC, which is brought over at its current angle of 60 degrees, because TAC is 30 degrees relative to the horizontal, which means it's 90 minus 30 degrees equals 60 degrees relative to the vertical. The third angle in the triangle between TAC and TAB is 80 degrees, because 180 minus 40 minus 60 is 80 degrees. There's a couple of photos showing how real cranes work. Real cranes are using more than two cables to lift up heavy boxes, because while two cables is stable in a plane, real crates aren't two-dimensional, they're three-dimensional. So in the upper right here we have 4 cables. In this picture in the upper left, it looks like we got 7 cables. Certainly some redundancy there for safety. The next thing we do in solving our problem is to use our force triangle in conjunction with either the law of sines or law of cosines to solve for the unknown forces, T sub AB and T sub AC. We have that T sub AB is to sine of 60 degrees as TAC is to sine of 40 degrees, as our 736 Newton force is to sine of 80 degrees. And you may be wondering, why do we use the letter T? Because the letter F is first letter of force. In this case, we're referring to T for tension, because normally forces in cables are called tension cables. Here's sample problem 2.6 for solving for forces in equilibrium. A designer wants to determine the drag force on a sailboat. She places a model of the proposed sailboat hull in a test channel and uses 3 cables to keep its bow on the center line of the channel. A diagram of this test channel is shown here at the bottom. The tension is 40 pounds here in cable AB, and it's 60 pounds in cable AE. And we want to determine the drag force, F sub D, exerted on the hull, meaning the force of the water flow resisting the sailboat from moving forward. And we want to find the tension T sub AC in the cable that connects point A to point C. We have some critical dimensions that are shown. It's 7 feet horizontally between points A and B. It's 1.5 feet horizontally between points A and C. And our model of our sailboat is right in the middle of the channel. It's 4 feet from the upper wall of the test channel and 4 feet from the lower wall of the test channel. First step is to calculate angles alpha and beta. The tangent of alpha is equal to its opposite over adjacent, which is 7 divided by 4, and that's 1.75, so that alpha equals 60.26 degrees. And the tangent of beta is opposite over adjacent, which is 1.5 feet divided by 4 feet. Take the inverse tangent, and beta equals 20.56 degrees. In step 2, we draw our free body diagram, which includes all the forces acting at point A, where point A is the front of the hull of our model sailboat. T sub AB is 40 pounds, and it's 60.26 degrees rotated from the vertical. T sub AC is unknown, but at least we know that its angle is 20.56 degrees rotated in the opposite direction from the vertical. T sub AE is pointed straight down, that's 60 pounds, and we don't know what F sub D is, but at least we know it's directly a horizontal force. Now we define our equilibrium equation, which we can do because by definition in this experiment the boat is not moving in the test channel, which means that the resultant R has to be 0, and if we add vectorially our four forces, TAB plus TAC plus TAE plus F sub D, we have to get a 0 vector. In step 4, we resolve the forces into their x and y directions, and then we're going to create two equations, summation f sub x equals 0 and summation f sub y equals 0, to solve for our two unknowns, which are T sub AC and F sub D. T sub AB is a known force of 40 pounds, and therefore its x component is minus 40 pounds, because that's going to the left, times the sine of 60.26 degrees. Remember, it's the sine because the 60.26 degrees is relative to the y-axis as opposed to the x-axis. And the y component of T sub AB is the 40 pounds times the cosine of 60.26 degrees, and it points up. Numerically then, T sub AB is minus 34.73 times I plus 19.84 times J. Units of force are used in pounds. Vector T sub AC does not have a known magnitude, and so we're going to keep its magnitude of TAC in italics, and we are going to multiply by the sine of 20.56 degrees to get its x component. So here's the x component of TAC. And the y component is TAC times the cosine of 20.56 degrees. And all we can do with vector T sub AC is have multipliers of its magnitude in I and j. So it's 0.3512 times magnitude T sub AC times vector I plus 0.9363 times the magnitude of T sub AC times vector J. F sub D is our drag force, and we don't know what its magnitude is right now. We do know, though, that it's a force in the positive x direction. It has some magnitude to be calculated. That's shown in italics as F sub D, and that multiplies vector I. In step 5, we can independently sum our x forces to 0 and our y forces to 0 because we're operating under the principle that the forces are all in equilibrium. T sub AB has an x component, which I highlighted in a red box, of minus 34.73, and a y component highlighted in a blue box of 19.84. T sub AC has an x component highlighted in a red box of 0.3512 times the magnitude of T sub AC, and its y component, which I highlighted in the blue box, is 0.9363 times the magnitude of T sub AC. T sub AE is minus 60 pounds times J because it's acting straight down here. And all we do is take these terms that I've highlighted for you in the red box and the blue box and set them equal to 0. So when we sum the x forces equal to 0, we find all the expressions that multiply I. And when we find the expressions that multiply by j, we get our second equation. And after this, it's just algebra to calculate what f sub d is and calculate what the magnitude t sub ac is. So here's your basic algebraic equations. There's your solutions, 42.9 and 19.66 respectively. Here's how we draw our forces in a force quadrilateral. So we start here with vector TAC, then add f sub d, go down for t sub AE, and then go up at a 60-degree angle for t sub AB, and we come back to the same point, which was point A. And here's an Excel solution showing the step-by-step calculations that I did in this problem. We can also find the rectangular components of a force in 3D space. We can draw a vertical plane OBAC containing force F. This plane passes through the y-axis, meaning the y-axis is contained in plane OBAC because line OB is along the y-axis. Force F makes an angle of theta sub y directly with the y-axis. Force F is also resolved into vertical components f sub y and vector horizontal component f sub h here in figure 2.25b, where this horizontal component f sub h is living in the xz plane. It's not along the z-axis, it's not along the x-axis, so we don't call it f sub x or f sub z. We call it f sub h because we're defining the xz plane as a horizontal plane in this three-dimensional picture. F sub y is equal to the magnitude of vector f times cosine theta sub y. F sub h, shown in italics, is equal to the magnitude of vector f times sine of theta sub y. Now we'll use vector methods for resolving the forces in the xz plane, as shown in figure 2.25c. This time we're going to use angle phi because that's the angle that f sub h makes with the x-axis. The magnitude f sub x is equal to the magnitude f sub h times cosine of this angle phi, and f sub z, which is the magnitude of our vector along the z-axis, is equal to f sub h times the sine of phi. F sub x is equal to the magnitude of force F times sine theta sub y cosine of phi, and f sub z is equal to f times the sine of theta sub y times sine phi. Using our Pythagorean theorem, we know that f squared is equal to f squared sub y plus f squared sub h. And we know that f sub h squared is equal to f sub x squared plus f sub z squared. And therefore, we can extend the Pythagorean theorem into 3D space. F squared, shown in figure 2.25b here, so there's our original vector f, equal to f sub x squared plus f sub y squared plus f sub z squared. Here we're going to show you how to find what are called the direction cosines of a force. The red colored box here in figure 2.26a in the lower left corner has magnitudes f sub x, f sub y, and f sub z for its edges. And the main diagonal of the box is this vector OA, and that's where our force F is. In right triangle OAD, we have angle theta sub x, and we see that f sub x is equal to f times cosine theta sub x. Likewise, in figure 2.26b, f sub y is equal to magnitude f times cosine theta sub y. And in right triangle OAE, so here's OAE of figure 2.26, f sub z is equal to f times cosine theta sub z. We can write a unit vector f as magnitude f sub x times I plus f sub y times j plus f sub z times k, and substituting for f sub x, fy, and fz, we can put our cosine theta sub x in there, and our cosine theta sub y, and our cosine theta sub z, and multiply respectively by I, j, and k. Those values, cosine theta sub x, cosine theta sub y, and cosine theta sub z, are known as the direction cosines of a force. Here is concept application 2.4 for our unit vector format. A force of 500 newtons forms angles of 60 degrees, 45 degrees, and 120 degrees, respectively, with the x, y, and z axis. Find the components fx, fy, and fz of the force. Express the force in terms of the unit vectors. We can determine the components of f because we're given the angles theta sub x, 60 degrees, theta sub y of 45 degrees, and theta sub z of 120 degrees. So we take our 500 newtons and we multiply in three independent equations times the cosines of the angles, and we get three values. 250 newtons, 354, and minus 250 newtons. And we can express the force in unit vector format. We just take our f sub x value of 250 newtons, multiply by I. We take the y component of 354 newtons, multiply by j. And we take the z component, minus 250 newtons, and multiply by k. In this slide, we'll show you how to calculate a unit vector lambda, which acts along the same line of sight as force F. In figure 2.28, force F is represented as the magnitude of F times cosine theta x times I plus the magnitude of F times cosine theta sub y times j plus the magnitude of F times a cosine theta z times k. We let unit vector lambda equal to cosine theta x times I plus cosine theta y times j plus cosine theta z times k. In the unit vector, the multipliers of I, j, and k are our direction cosines. Force F is equal to magnitude F times lambda. Therefore, lambda and force F have the exact same line of sight because they're pointed in the same direction. From our 3D version of the Pythagorean theorem, we know that the unit vector lambda squared is equal to lambda squared sub x plus lambda squared sub y plus lambda squared sub z, and that's equal to 1 because the length of lambda is 1. Therefore, cosine squared theta sub x plus cosine squared theta sub y plus cosine squared theta sub z equals 1. Here's concept application 2.5 for direction angles. A force F has components f sub x equals 20 pounds, f sub y equals minus 30 pounds, and f sub z equals 60 pounds. Determine the magnitude F and the direction angles. We know that the magnitude of F is the square root of f sub x squared plus f sub y squared plus f sub z squared. And when we do the math on our components of 20 pounds, minus 30 pounds, and 60 pounds, we find that the magnitude of F is 70 pounds. In step 2, we find the direction cosines. Cosine theta x equals f sub x over f, so that's 20 over 70. Cosine theta y is f sub y over f, so that's minus 30 over 70. And cosine theta z equals f sub z over f, so that's 60 over 70. And when we take our cosines of those three terms, we get directly our direction angles, which are theta sub x 73.4 degrees, theta sub y 115.4 degrees, and theta sub x equal to 31 degrees. Now we'll show you how to define a force based on its magnitude and 2 points on its line of action. In figure 2.29, force F is defined by a magnitude of F and the fact that it connects points M, which has coordinates x1, y1, and z1, and point N, which has coordinates x2, y2, and z2. We define vector Mn equal to dx times I plus dy times j plus dz times k, where the values of dx, dy, and dz are respectively the differences in the coordinates between point N and point M. And it's important to know the order that we do the subtraction, because point M is the first point, x1, y1, and z1, and point N is the second point, x2, y2, z2, you have to calculate dx as x2 minus x1, dy as y2 minus y1, and dz as z2 minus z1. The easiest way to remember which point is point 2 and which point is point 1 is the fact that the arrow for force F and the arrow for vector lambda is pointed towards the second point. So here's your arrow, and it's pointed towards point N, which is the second point, x2, y2, z2. D is the magnitude of Mn, and it equals the square root of d squared sub x plus d squared sub y plus d squared sub z. We define unit vector lambda as equal to vector Mn divided by the length of Mn. So that's vector Mn in terms of its I, j, and k coordinates divided by d. Further algebra shows that lambda is just 1 over d times dx I plus dy j plus dz k. And because force F is defined as magnitude F times lambda, force F equals the magnitude F divided by magnitude d times dx I plus dyj plus dzk, which means that the x-coordinate f sub x is f times dx over d, f sub y is f times dy over d, and f sub z is f times dz over d. But in the prior slides, we defined fx as equal to f cosine theta x and fy equal cosine theta y, and fz equals cosine theta z. So now we have new definitions for the direction cosines. Cosine theta x is equal to dx over d, cosine theta y is dy over d, and cosine theta z is equal to dz over d. Let's illustrate how to define force F with a sample problem 2.7. In this problem, a tower guy wire is anchored by means of a bolt at point A and connected to the top of the tower at point B. The tension in the wire is 2,500 newtons, and that tension acts up to keep this tower from keeling over and falling down in a counterclockwise direction. The arrow for force F and unit vector lambda is pointed at B, which means that B represents point 2 and its coordinates x2, y2, z2, and A on the ground represents point 1, which is x1, y1, and z1. And our first step in defining x is to calculate dx, dy, and dz. dx equals x2 minus x1, which is the x-coordinate of point B minus the x-coordinate of point A. Point B is at x equals 0. Point A is at x equals 40 meters. Therefore, dx is minus 40. dy equals to y2 minus y1. Point B is located at y equals 80 meters. Point A is located at y equals 0, and therefore dy is equal to 80 minus 0, which equals 80. And dz equals z2 minus z1, where point B is z2 equal to 0, and point A is 30 meters on the negative z-axis, and therefore the z-coordinate of point A is minus 30, and 0 minus minus 30 equals 30. Therefore, dz equals 30. Here's what real guy wires look like on a radio tower. This radio tower is a good 50 meters up in the air, and it's not just held by one guy wire, it's held by 18 of them. So at each of 6 points going up and up and up the tower, there are 3 guy wires spaced 120 degrees apart. You can bet that the designers weren't fooling around and didn't want this radio tower to fall on houses in the neighborhood. And it's my neighborhood. And I checked to see on Google Maps, how far is this radio tower at the base from my house? Is it at least 50 meters away? And suffice to say that I calmed down when I found that my house is a great deal more than 50 meters away. So even if this tower fell down, at least it wouldn't hit my house. In step 2, we calculate the distance between points A and B, which is represented by small d. AB is the length of vector AB, which is the distance between A and B. That's also equal to small d, the distance. We take the square root of d squared x plus d squared sub y plus d squared sub z, which is 80 squared plus 40 squared plus 30 squared. Take the square root of that, we get 94.3. Now we define vector AB and unit vector lambda. Vector AB is equal to minus 40 meters, meaning dx in I, plus dy in j, plus dz in k, which is why we just plug in minus 40, 80, and plus 30. And lambda is vector AB divided by its length, where the length is small d, which is 94.3 meters. We also know that vector F is the magnitude of force F times lambda, and substituting for lambda, vector F is equal to the magnitude of F times vector AB divided by length AB, which is 2,500 newtons divided by 94.3 times vector AB, where vector AB is shown here on the right. And when we do the math, we find that vector F is equal to minus 1060 newtons I plus 2120 newtons in J plus 795 newtons in K. We've just calculated the values of Fx, F sub y, and F sub z. We can easily calculate the direction cosines. Cosine theta sub x is minus 1060 newtons, which is F sub x, divided by 2,500 newtons, which is the total magnitude of force F. Likewise, calculate cosine theta sub y and cosine theta sub z. With those 3 direction cosines, we just take the arc cosine to find the angles. Theta sub x equals 115.1 degrees, theta sub y equals 32 degrees, and theta sub z equals 71.5 degrees. Here's an Excel solution that shows the step-by-step calculations. A particle is in equilibrium when the sum of given forces is 0. And we showed that before in 2D space in a plane. But it's also true in 3D space, or else Isaac Newton wouldn't be so famous. We can represent that by vector r is the sum of vector f, and that equals 0. And you solve the 3D force problems by resolving the forces into x, y, and z components. Then you individually apply the equations summation f sub x equals 0, summation f sub y equals 0, and summation f sub z equals 0. You then obtain 3 equations in 3 unknowns, which you can solve using your high school algebra, or if you learn matrix determinants in high school or in freshman year in college or sophomore year in college, you can use that too. The methods are equivalent, you'll get the same answers. To illustrate that, we have sample problem 2.9 for the equilibrium of 3D forces. In the figure at the bottom, a 200 kilogram cylinder is hung by means of 2 cables, AB and AC, that are attached to the top of a vertical wall. A horizontal force P, perpendicular to the wall, holds the cylinder in the position shown, suspended slightly above the ground. Our job is to determine the magnitude of force P and the tension in each of the cables AB and AC. Point A, which is the top of the cylinder, is acted upon by 4 forces, including its own weight, represented by the mass 200 kilograms. You can use our geometry in this diagram to express the tension TAC and TAB in terms of its X, Y, and Z components. And then you apply the equilibrium conditions to calculate the tensions. In step 1, we draw our free body diagram, choosing point 8 as the free body. We see vector TAC going from A to C with its unit vector lambda AC, and we see vector TAB representing the tension in the cable going from A to B, and its unit vector lambda AB. We have the weight W is the weight of the 200 kilogram cylinder expressed in newtons. That goes straight down in negative y direction, and force P goes in the positive x direction. When we introduce unit vectors I, J, and K, the 2 easy ones are P, which is equal to magnitude sub P times I, and vector W, which is equal to minus mg times J, where m is the mass, 200 kilograms, g is our gravitational constant, 9.81 meters per second squared, and that equals minus 1962 newtons in J. The minus sign indicates that gravity is pulling the weight down in the minus y direction. For vector TAB, we first need to find the x, y, and z components of vector AB, where the unit vector along AB is lambda sub AB. And once again, we have to be careful how we define dx, dy, and dz. Because unit vector lambda points towards B, B is the coordinate expressed by x2, y2, and z2, and point A is the coordinate expressed by x1, y1, and z1. dx equals x2 minus x1. B, point B, has a value of x equals 0, and point A has a value of x equal to plus 1.2. Therefore, dx equals minus 1.2. dy equal to y2 minus y1 is equal to the y-coordinate of point B, which is 12, minus the y-coordinate of point A, which is 2. That equals 10. And dz is the z-coordinate of point B, which is 8, minus the z-coordinate of point A, which is 0, d sub z equals 8. We express vector AB by putting dx in front of I, minus 1.2 meters times I. We plug the dy component 10 in front of the j, and we plug in the value of a dz, which is 8, in front of k. We find the length of vector AB is the square root of d sub x squared plus d sub y squared plus d sub z squared, which is 12.862. We express lambda AB as vector AB divided by its length. So we take respectively the minus 1.2 and the 10 and the 8 and successively divide them by 12.862 to get the values of multipliers shown in the second line of I, j, and k. And vector TAB is the magnitude of T sub AB times lambda sub AB, but we don't know yet what the magnitude of T sub AB is. So we leave it in there as a variable. For TAC, we use the same methodology to find the x, y, z components of vector AC that we did for vector AB. Note that unit vector lambda is oriented from point A to point C, which makes point C the x2, y2, and z2 point, and point A is the x1, y1, z1 point. Therefore, dx equals 0, which is the x value of C, minus 1.2, which is the x value of A, and that equals minus 1.2. dy equals y2, which equals 12 for the y value of point C, minus 2, which is the y value at point A, 12 minus 2, that equals 10. And dz equals z2 minus z1, which is minus 10, because the z-axis where C is in the negative region, minus 0 equals minus 10. The vectors AC, lambda AC, and T sub AC are formulated exactly in the same method as T sub AB. You'll get three constants. One multiplies TAC times I, a second multiplies TAC times J, and the third constant for force T sub AC multiplies magnitude TAC times K. We write the equilibrium equation, which sums the forces to 0. There's four forces, T sub AB plus T sub AC plus P plus W equals 0 in vector format. And we gather the equations we created, which involve the unit vectors I, j, and k. There's four of these equations in play. And the next job is to take the equations and sum the terms that multiply I, sum the terms that multiply by j in these four equations, and sum the terms that multiply k, and separate them out into one vector equation. So all these terms multiply I, and these next three terms I'm showing with my mouse multiply by j. The last two terms multiply by k. When you look at what the terms are, there's three variables in the terms, p, t sub ab, and t sub ac, and they're sprinkled around the different multipliers of I, j, and k. Now we form three equations with three unknowns in algebraic form by setting the sums of x, y, and z forces to 0, and those sums are simply the respective multipliers of I, j, and k. Now we have three equations and three unknowns, and you can solve them by algebra or matrices with determinants or any other way you use to solve multiple equations and multiple unknowns in your math careers. And you get P equals 235 newtons, T sub AB equals 1402 newtons, and TAC equals 1238 newtons. Here's a little bit of brute force algebra that I did to prove it out. And there is your Excel solution to sample problem 2.9, showing the flow of calculations and the numerical results received.